It's great to be here. I'm going to start with Paul Tullis, who is a journalist specializing in long-form pieces for national magazines. He's written about science, technology, commerce, and their intersections for the New Yorker, the New York Times, Nat Geo, Bloomberg Business, Scientific American, Nature, Wired, and many others. Most recently, he published his article, "The Brain-Computer Interface is Coming, and We Are So Not Ready for It," in the Bulletin, where he's exploring potential advances and pitfalls of merging the human mind with a computer one, which we'll be talking about today. We then, very exciting as well, Paul, so exciting to have, Amy Orsborn, who really is at the forefront of this at the laboratory and research level. She is a Clare Boothe Luce Assistant Professor in Electrical and Computer Engineering and Bioengineering at the University of Washington. She works at the intersection of engineering and neuroscience to develop therapeutic neural interfaces to restore motor function. Her lab explores neural interfaces as adaptive closed loop systems that engage plasticity in the brain and the spinal cord. She designs engineering approaches that shape neural adaptation to improve system performance and uses neural interfaces as a tool to study brain learning. Among her honors, many honors, she received a L'Oreal USA for Women in Science postdoc award, the L'Oreal USA Changing the Face of STEM award, a Google Faculty Research Award, and is an interdisciplinary rehabilitation engineering research fellow. Welcome, Paul, and welcome, Amy. I wanted to start because Paul's piece really gets us into navigating these thick and kind of thorny issues from the perspective of neuroscience and the brain-computer interface and the brain-machine interface. So Paul, I kind of wanted to just start and give you that open-ended question of what kind of sparked your curiosity as a journalist and got you into reporting about the brain-computer interface.
Right, thanks. I first heard the term brain-computer interface about 3.5 years ago. I was attending the Milken Global Conference, which is sort of a Davos West held annually in Beverly Hills by the Milken Institute, which is a sort of think tank founded by the former financier. And they have a session each year called Things That Will Blow Your Mind. And featured at this session were a couple of founders of companies that were involved in developing brain-computer interfaces. I had no idea that such a thing existed or was, on the menu, and was pretty astounded by the presentations. And I immediately saw the ethical implications were immediately apparent. Given the appearance by Mark Zuckerberg of Facebook before Congress, at which he actually, I'm not sure that this had happened yet, but anyway, it occurred to me while I was doing the story. He was asked, one of the senators grilling him didn't know how Facebook makes money. And I thought, well, given that level of technical sophistication in Congress, we should perhaps be concerned about our ability to grapple with these issues. So anyway, after I attended that presentation, I did what any good journalist would do, and I sat on the idea for about 6 months and did nothing. And then I started poking around and looking for ways in to tell the story of how these were being developed. And that appeared with the next generation neurosurgical, I'm forgetting now it's the program's next generation non-surgical neurotechnology program, or N3. It's a $104 million program run out of DARPA, the Defense Advanced Research Projects Agency, which has given a bunch of money, $104 million, to 6 research groups trying to develop non-invasive BCIs. As I got into it, I learned that there are a lot of, it's a rather fluid concept. The more that commerce gets involved with technology, the broader the definition of these things become. You see that with AI and other things. A lot of companies are out there selling what they call a BCI, which is basically just an ECG that helps you play video games. But there are also things that are in process now where in research programs around the US where people have devices implanted in their skulls, in their brains, which reads neurons and detects intent of motor function. And that's helping people with paralysis, EEG and ECOG, which is sort of a finer resolution version, which is planted, sort of layered over the surface of the brain. That's being used to collect activity from a larger area. So it just became apparent that, that this thing is happening now, and that while we might be a way off from some of the, sort of science fiction scenarios that you might be able to imagine, the ability of our society to, we don't have a great track record in dealing with new technologies and their implications, and that, now might be a good time to start talking about it.
Well, that's great, because I think it sounds like the goal is to try and not allow these technologies get out in front of the policy, like to try and get the policy up to speed. And that kind of in your work here in this piece, if 2017 was the Milken conference, I think it's really important to try and continue to educate the public about this is part of journalism on a continuum, right? You published multiple stories between 2017 and now, and it was that spark of an idea that starts at Milken. And can you give us a little bit more insight into how your piece kind of distilled and kind of encapsulated what looks like a very rigorous and fast pace of like 18 to 20 months, where you're looking at the more invasive, and then by the end of the reportage, you have access to show that this is about to make that leap to what we discussed in prior meetings, to the non-invasive, and that publicly it looks like the acceptance on a policy and a clinical level is really these non-invasive. Can you talk a little bit about that work, that you accessed laboratories as well as entrepreneurs in this space while the technology is just rapidly changing from invasive to non-invasive?
Yeah, so the non-invasive is really the holy grail for this technology. Currently, to get the functionality of using thought to control your body, you need brain surgery, and that's not something that everybody is going to sign up for. Even, I talked to somebody who's paraplegic, who said that he's spoken to other people with his condition, and even they wouldn't want to have an additional surgery to have this ability, limited as it is at this time. So there's, like I was saying, EEG has been used for several years to train patients who've suffered a stroke to regain motor control, and more recently for things like video games. That is, sensors are placed outside the skull, and it's very rough. So somebody used the analogy of it's like being outside a stadium. You can hear the roar of the crowd, but you can't hear, whether individuals are speaking or what they're saying, or, whether it was a 2-yard touchdown run or an 80-yard pass. ECOG is a bit more specific. It's used to measure brain electrical activity during attempts to diagnose tumors, seizures, stroke. It's a flat, flexible sheet placed onto the surface of the brain inside the skull to collect activity from a larger area immediately beneath the sensor sites. And then there's also currently something called a Utah array, which sort of looks like a tiny bed of nails about the size of your pinky fingernail. And that has hundreds of sensors on it that detect activity from neurons. And that's best so far in terms of body control. But like I was saying, and as you suggested, what everybody's really after is non-invasive. And that's difficult because the skull is, it's designed to protect the brain, and in so doing, it protects the brain's activity as well, of course. And it's really hard to get light or and I'm sure Amy would be better positioned to talk about this, but it's really hard to get information from inside the brain, through the skull, essentially. And so that's what this N3 program out of DARPA was designed to do. And some of the people that I met with, they say they're making progress. They work with skull simulators, a piece of artificial material, or sometimes a dead skull doesn't work, apparently. It doesn't have the same electrical properties. So they use an artificial material. And they're working with various techniques. Some are using light, some are using ultrasound, some inject nanoparticles, some use a variety of methods, some to, one to read, one to write, that is, deliver information to the brain and then get information out of it. But they say that they are making progress in the lab. And if they can get through the skull, then, that's the next challenge. And then figuring out, if it works and how deep they can get and what level of thought. It's one thing, I talked to the paraplegic that I mentioned, or the person with paraplegia that I mentioned. He has to work really hard to think into the machine to get it to make his hand do what he wants it to do. And so it's a long ways between even being able to read or write through the skull and being able to, to determine complex thought, like what do you want for breakfast or stuff like that.
And that's the engagement, right? Is trying to understand is it ingoing or outgoing? And in terms of the internal process. And I think thinking about the disabled and the ability community, if we jump over to Amy, who might be able to open our eyes a little, your laboratory, one of the things I really love about the description is that you're learning engineers. And I just thought maybe we could hear a little bit from you before we get at 30,000 feet, before we get close to the ground. In your research and academic career, I'm kind of interested how you got to this space of engineering and neuroscience, and give us just a little lay of the land there and kind of where you pivoted to create this cutting edge laboratory that you have.
Yeah, sure. So I like to say that I ended up in this field in a lot of ways by accident, or sort of by being in the right place at the right time. That I sort of learned about, unlike Paul, I learned about brain-computer interfaces when I was in college, because I happened to go to a talk that actually was given by a professor here at the University of Washington, Eb Fetz, who was a pioneer that in many ways created one of the early examples of a brain-computer interface. At the time, he was actually trying to answer a very simple scientific question about what neurons in the brain were doing. But to do that, created a circuit where he could read out the neural activity and ask the monkey that he was, whose neurons he was recording, to control a dial. And that basically is a brain-computer interface. And so I learned about those experiments he was doing, and I was just, similar to Paul, I was just sort of like, this is insane. This is really interesting. And
were you at an engineering training at that point? I'm just kind of curious how you get to neuroscience from electrical and from it. Can give us a little idea.
Yeah. So I was a physics major at the time. So this was in college. And I always enjoyed biology, and I liked the idea of, I was motivated by the applications of biology, of sort of trying to create healthcare solutions and improve care for people. But at the end of the day, I really liked math. And so I kind of gravitated towards physics and engineering. And so then when I went and I saw this talk, I sort of realized and learned about engineers that were working in this space of neuroscience, I kind of learned that that biology wasn't just, that there was a way to marry basically biology and science, or biology and math. And so that was for me kind of a lot of what clicked and led me in this direction. And so then I started reading kind of, I looked up what DARPA was funding at the time, and there was funding in this space early on. And I kind of found all of the, did some reporting myself of who's working in this space, what's going on, and then I used that to apply to graduate school. And so then from there, I kind of, basically the more I learned about this field, the more I just found it really fascinating. So that kind of was my hook in.
Wow, it's really a testament to how we have to really pull these emerging scientists in at the undergrad level too. That's great. Can we talk about one of your projects right now, kind of expanding on that, the neural matrix? You published in Science earlier this spring that it, quote unquote, might be scalable to humans for clinical purposes. Can you give us a little bit of an outline of that technology and where it's at today?
Yeah, sure. So like Paul mentioned, there's lots of different ways that you can measure activity from the brain. But one of the biggest challenges, so in addition to kind of this issue of where you place the sensors, so invasive versus non-invasive, there's also an issue of just basically bandwidth. How much information, how many sensors can we put on the brain, then get them digitized and out. And one of the biggest problems there is that neurons are really small. And so you want, and there's lots and lots of them. And so you want a lot of sensors, but all in sort of a very small space so that you can listen to all of the individual neurons. But that then leads to a problem if you think about having thousands of wires coming out of a tiny space that's, the size of a millimeter, that you end up with a cable that's bigger than your sensor. And so there's all sorts of really interesting challenges kind of in this space. And so the piece that was addressed by that work is a collaboration between the lab that I was working with at the time in my postdoc, Bijan Passaran at NYU, then John Viventi at Duke University, and John Rogers. So this is sort of a big team of people that span material science, electrical engineering, and then also neuroscience, work together to come up with a strategy where you actually create a device that has active electronics on it so that you can multiplex the signals. So you
explain multiplex to me.
Yeah, so by multiplex, I mean that if you have two sensors, but you have one wire, you can flip the connection back and forth with one wire, sort of still sample two of your sensors at the same time, just by, you sort of have half of the sampling rate, right? So because you're alternating back and forth, but you're listening to one sensor at one time point and the other sensor at the other time point. And then you can combine the signals afterwards.
And where is the agency? Like and where are the sensors being controlled from? Is it dual? Is it the individual, or is it an external?
Yeah, so that in this device, that's all external. So the technology is just sort of deciding, exactly how you are sampling from this larger bed of sensors. But so this is kind of the key piece of this technology is that it does potentially allow for scaling, right? So we have this issue that we kind of can't increase the number of sensors that we have in a reasonable way because all of the other electronics on the other side get really big and bulky really fast compared to the size of our sensors. And so this opens up some new pathways to have technologies that could scale, which become really important when you think about humans. Because humans have really big brains compared to a lot of the animal systems that are currently used for developing these technologies.
That's great. And can we talk then, and trying to engage both you and Paul on this, maybe a conversation about how we go from animal studies to human clinical, and what that looks like. And I think, Paul, in your piece too, you have some great, especially with the N3, talking about there's ethical landscape issues, safety issues. I'm just going to kind of throw that out to the two of you to kind of discuss. Do you want to start with do you want to start with that, Paul, and then kick over to Amy? Because I remember in our pre-discussions, we thought that would be really interesting to kind of hear.
Yeah, I didn't want to interrupt. The N3 program, they've talked to the FDA and they've decided that the minimally invasive techniques, those involving nanoparticles, those need to show that there will be some benefit to health in order to proceed with human trials, and the others just need to show that they're not going to be harmful. And this is new territory. So how the FDA's got a full stack of issues that it's dealing with now, and I've dealt with this in other stories where they're having to deal with new technologies all the time and the issues that they raise, and for human trials, and this is going to be one of them. But maybe
a medical device too, right, for the FDA, and this gets into that hybrid of technology and a medical device, which Amy, you've talked about the medical device and the threshold at the FDA in terms of the community of people who may have lost usage based on accident, trauma for our veterans, and people wanting to garner it for the first time, perhaps who were born without some of these capabilities. And the FDA is in their panels, in their advisory panels, are trying to look at these neuroscience medical devices with a little bit more of a holistic approach. Can you talk a little bit about that from your laboratory? I know you. I don't believe you've submitted yet to FDA, but just that landscape very well.
Sure. Yeah. So I think there's a couple of things that I'll just sort of point out or comment on. So one is that right now I would say the vast majority of work in this space is definitely focused on targeting this populations of people that have some sort of neurological disorder or injury, right? And they're trying to then restore functions that have been lost. And so the vast majority of clinical trials, for instance, that are in this space are then working with devices that have been approved, sort of similar to what Paul commented on, just based on that they don't cause harm necessarily, that they're safe to use. And so then the Utah array, for instance, that Paul mentioned earlier, is a great example of a device that is FDA approved, that now has been really powerful in then testing these brain-computer interfaces for restoring motor function in people that have some sort of neurological injury. And so there's some really fantastic work from a couple of different clinical trials where they're working with these populations of very brave volunteers that engage in these studies, so that we can then learn how to deal with the signals, right? Because there's sort of two pieces of the problem in many ways when you think about an ultimate brain-computer interface. There's first the issue of getting the information out, but then there's also the issue of what do you do with the signals afterwards to make a useful therapeutic device. And so I think kind of I guess it's worth kind of potentially making that distinction, that most of the FDA approvals are kind of focused on the device itself, right? That's not, that's interacting directly with the biology for getting the information out of the brain, that's not harmful, right? And that's safe. But then there's this extra question of the ultimate therapeutic benefit of the entire system, right? Once you have what you do with the measurements, once you have them. So I think that's an interesting question then of how exactly the FDA will approach that regulatory space. I don't actually know the details of how that would how those things would be evaluated, but it's a important distinction to recognize.
And on the subject of what you do with that information, that's a really important one. As Amy said, you know, right now it's mostly being used to help people with medical conditions, and you know, the possibility of curing paralysis is obviously a very tempting one. But you know, I was at the applied physics laboratory at Johns Hopkins talking to some guys who had been working on another DARPA program called Revolutionizing Prosthetics, which led to a lot of interesting brain-computer interface technology. They basically were able to, and I think Amy referred to one of these before, they are able to hook people's brains up to a robotic arm and get the arm to do what, you know, they think into it, so to speak. And I was listening to these people describe this thing, and I was like, wait a minute, if you can get it into a robotic arm, you know, and the arm is attached to his wheelchair, first of all, it doesn't need to be a robotic arm, it can be anything. And second of all, it doesn't need to be on his wheelchair. It could be in the next room. It could be on another continent. It could be on the moon. And they were like, yeah, once you get and this was so obvious to them, they were like, yeah, once you get the signal out of the brain and digitize it, you can do whatever you want with it. And so as far as, you know, potential harm to humans, you know, DARPA, obviously, you know, they're interested in this initially for helping, you know, vets with who've lost limbs in combat. But they were also frank with me in saying that they intend to weaponize this essentially. They want a soldier or air person to be able to use their mind to control a swarm of drones. And, you know, that you talk about harm to human health, there's been a lot of harm to human health from drones among civilians in Pakistan and Afghanistan. So, you know, that's just one of the things that I think that we need to start thinking about. And that people, I'm sure the neuroethicists that Amy works with have already started thinking about, you know, once you get the signal out of the brain, what are you allowed to do with it?
Can we talk about that, Amy, the neuroethics lab and these dual use technologies?
Yeah, that's so I think Paul's exactly right that, you know, as the technologies advance and our ability to interact with the brain, you know, that technology is sort of coming to fruition. And so now there's, I think, a lot of interest and thankfully increasing interest, I would say, among the scientific community for thinking about these ethical questions. So I'm here at the University of Washington, and we have a Center for Neurotechnology. That's a center that was funded by the National Science Foundation for neural engineering research here at UW. And one of the key pieces of that center is actually a neuroethics team. And so there's a group primarily centered and based in the philosophy department, but that's at University of Washington. I believe we have collaborations as well with University of San Diego, or San Diego State University, excuse me, and MIT. But there's sort of a collaboration of people that where the ethicists are kind of embedded within the laboratory. So I think this is a really fantastic model where the ethicists are kind of working with us to understand the technologies that we're developing and thinking a little bit ahead to some of the implications, and then also working with the scientists directly, you know, to sort of start planning how would we maybe modify this device, for instance, to make it more secure or to make a patient feel like they have agency over this device that's interacting kind of directly with a very private part of themselves, like their brain. So
That's a great insight. And Paul, you were inside laboratories. You accessed companies through entrepreneurial business ventures. Did you hear this discussion or see it, witness it between the business and the science? Give us some of your.
They all are cognizant of these issues, and they work with most. I couldn't name any that I know that does not work also with neuroethicists. Other people outside the program the programs are concerned that a lot of the funding for this is not coming from publicly funded organizations like the NSF, but is instead coming from, well, I mean, defense, of course, being publicly funded, but it's not being primarily a scientific organization, and they wonder whether money coming from the military is going to lead to something worrisome. And then also, of course, Facebook has a whole team working on non-invasive BCI. They have piles of money that can, tempt people away even from institutions like MIT with deep pockets. And so, and then they're, less transparent than a research university. So the teams that I talk to, yes, they're talking to neuroethicists, they're working with neuroethicists, but others outside the programs are concerned that, if the funding for these projects is coming from the private sector and the military, then it may be more likely to lead places that we don't want it to go than if it's coming from a more scientifically minded organization.
Great. Well, that's a very good point. I think we can definitely delve more into the idea of how public-private partnerships play out in this in the next 20 minutes, but I'm going to throw it back to our coordinator, Hallie.
Thanks, Dawn. Hello again. As a reminder, my name is Hallie Posner, and I am the program coordinator here at the Bulletin. We do ask that you please keep yourself on mute throughout the program unless you are called on for a question. But please keep your cameras on as we are striving to build a community, and all of you are members of our community. If you have a question for our speakers or moderator, please use the raised hand function. Our moderator will see that and call on you. You can find this by clicking on the participants button at the bottom of your screen. Please do not physically raise your hand. There are too many participants for us to recognize you in that way. Also, please note that we have many folks on the call, so we apologize in advance if we do not get to your question. If you have already raised your hand, rest assured we see you, but are unlikely to get to all questions. A recording of this program will be available on our website in the coming days. Back to you, Dawn.
Great. Well, I see Arthur DeForest has raised his hand, so let's hear our first question from Arthur.
Yes, can you guys hear me?
Yes.
So if you're taking into consideration the common usage of a phone and the amount of data that's being gathered through companies, well, let's stick with Google for now. And then you ask yourself the question, would I rather have someone read the content of my brain or read the content of my phone? There is like an inherent flaw in the human brain that would just make it like the phone knows much more about you than your brain remembers about you. And so I'm thinking, how do you think, and that goes to both Paul and Amy, how do you think that the brain interface will change this idea of like, would it even matter? Like the ethical question behind being able to read and receive data from the brain directly. Is that even a moral issue, given that a simple phone knows already so much about you that your brain can't even remember?
Yeah, I think you raise a really great point, and one that I've thought about myself. I think sometimes in some ways we overprivilege the brain, right? We think of it as very somehow very special, but companies like Google and others have demonstrated that even just observing behavioral data of people can tell you so much about a person. And in some some cases more than what we neuroscience can yet tell you from just looking at your brain, right? We're not able to necessarily predict with the same accuracy as Google can, for instance, just by watching your behavior and having information from hundreds of thousands, millions of people. So I think in many ways there's the ethical questions are not fundamentally distinct necessarily. I think there are differences, sure. But I think that it's worth recognizing that a lot of the ethical questions that people think of in neural interfaces are also ethical questions, you know, that you might want to think about when it comes to big data and sort of data monitoring in general.
I think that there's a lot on your phone, certainly, and there's a lot in your brain. And I think that there may be stuff in your brain that even your phone doesn't know about you, and that you might not have, be willing to put on your phone. One of the researchers I spoke to, Jack Gallant at UC Berkeley, mentioned, you know, we all have these latent desires or thoughts that we might be ashamed of, but and we would never voice or write down, but they're in there somewhere, and they're gettable. He said the only thing that that it seems they would not be able to get are things that you remember, but you don't know you remember. Like, you know, if I asked Amy, what was the name of your 5th grade math teacher, you might have to think about it for a minute, and then you would, you know, be able to come up with it, or maybe a few days later it would pop into your head. That kind of thing is very difficult to get, but virtually anything else, in terms of the physics of it, there's nothing keeping people from getting at it through technology eventually.
Thinking like biometrics already, I think that Arthur is probably thinking of as well around Google. Can we also now hear from Mary Jane Williams? And Mary Jane, will you let us know where you are joining us from?
I'm in Orlando, Florida, crazily enough. Here's a question. Are we headed toward worst case scenario down the road where X or Y can actually plant an idea into, for example, 2 people inside a Minuteman missile silo to tell them to launch a missile, or even into our president's mind to launch a missile? Are we headed that way? And if not, what's the barrier that's keeping us from getting there?
That's a great question that didn't come up in my research. I think that the target would need to have a BCI installed, right, Amy?
Yeah.
Be hacked?
Right.
Theoretically?
Exactly. I think that this gets into sort of questions of, because I think I saw in the chat somewhere, scroll by a question about sort of whether brain-computer interfaces could be hacked. And so certainly in principle they could, and this is kind of a piece, I think, of in the forward thinking of the technology, right? We need to design the electronics and the software in such a way that they have encryption, right, to sort of protect them and make them secure. So that's kind of one piece of it. The other, in terms of the kind of science of where we are, what we would need for Mary Jane's proposal to you know, come to fruition, I think we do know something about the sort of read out and write in, right? We know we can, for instance, stimulate the brain to elicit movements or things like that, or to change someone's behavior. But I think right now, most of those things are still somewhat crude. So the idea of like a thought, right, is very abstract, or like a desire to perform a specific action. I think there's still a lot that we would need to understand about the brain to kind of evoke complex series of actions, for instance. But in principle, the possibility would be there.
They would be there.
Yeah, yeah, but so then I think the question becomes then the importance of security, right? And sort of making it such that the devices were not were protected from, sort of outside interference.
And provided, of course, that the target has a BCI implanted that can.
Right. Yes.
So it looks like malware for the brain is where we're going. Thank you. Great question, Mary Jane. Can we now go to a raised hand with InstaHub? Tell us where you're joining us from.
Sure. Hi, thank you. Joining from Philadelphia in the United States. Thanks for taking the time in the talk. Just bumping the question I had in the chat, which was, so there are obviously a lot of academic and clinical researchers working on technologies that can be used for neural interface for different applications. And, with a decent good faith interpretation, you can imagine that a lot of them are interested more so in the clinical benefits, and in which they are there. We've seen them from everything from cochlear implants to some of the potential applications of what we've talked about today. So, is there anything practically that these researchers, given that the technologies are in these early stages, is there anything practically that they can do in addition to communication with neuroethics departments to limit the opportunities for weaponization that have been kind of brought up, especially for these military funded projects where the intention may be good, but obviously due to the context in which the technology is being developed, the worst case scenario of weaponization seems pretty high. Is there anything that the researchers can do on their end to kind of limit that, while not without necessarily just stopping the research wholesale, which would be kind of the ultimate approach?
Amy, do you want to start? Great question.
Sure. Yeah. So thank you for that question. I think it's a great one, and definitely one that I think about myself. I think for me, a lot of my approach or thinking about this is really sort of like I mentioned, thinking about the system as a whole, right? So for example, I don't work on encryption and hardware and things like that. I work more on the algorithms for how we interpret neural signals, for instance. But as my technology advances, I need to be thinking forward to the potential applications, and then working, with folks to, for instance, make sure that the ultimate device would be secure. Or that there might be, because we all work on little pieces of the system, right? I think you have to kind of think about how it plays into a broader whole, and potentially anticipate. I acknowledge that that's sort of a little bit slightly hand wavy, but I think it's you raise a question that's kind of always a concern for scientists in general, right? That like, how do you plan for an unknown future, right? Or what someone might do with a discovery that you have that has consequences that are difficult to anticipate at the time.
Is there a way, Amy, where you talk about how the ethicists are working kind of embedded along the way of the medicine and technology? Have you seen, or is there argument to be made then that you also need to have sort of encryption experts? You need to have that look about from the safety both of bad actors garnering control of these devices, these BCIs, but also simultaneously preventing someone themselves with a BCI becoming the bad agent, I guess, or bad actor.
Yeah, I think that that's a great point, and I think that sort of speaks to the need. Sort of another way to say what I was talking about is that as these technologies mature, basically researchers need to start working as integrated teams, right? Where all sort of parties that might have important input are considered, are there, right, at the table, able to contribute. So security experts, for instance. I also actually think that in addition to, maybe embedded neuroethicists, I also think probably one thing that we need to do that I don't yet see as much of personally, that doesn't mean it's not happening, would also be having policy folks present as well. So thinking about, for instance, militarization of these technologies. I think having people that work, in policy kind of embedded, with these technologies might be valuable.
I think we've seen some of that in synthetic biology, right, with the National Academy of Sciences and CRISPR. So maybe the time is beginning to open up in this field because the technology and the science is advancing. Yeah, and Paul, you were inside, again, as a journalist, I say I bow to you because the access and the trust that you garnered really is for this explanatory deep dive kind of journalism. You just had so much exposure. Have questions like this were questions like this you asking of your sources and your subjects, but also this kind of sci-fi reality, whether Manchurian Candidate, the Thought Police, and Minority Report. Where do you come out at this point of having filed this piece? And I feel like it's sort of in your DNA now. It's kind of living with you still. Yeah, well,
it's not the type of question that you want to ask a scientist when you first walk into the room. First you want to ask them, so how's it work? But once you've got everything that you need, you can bring up the thornier issues, like, so is this going to lead to the dominion of humanity under the thumb of technology? Fortunately, I did learn that there are a lot of groups working on this. One of the people I spoke with, a guy named Boothe at Carnegie Mellon, who developed the first non-invasive BCI that was able to track a computer cursor on the screen without any delay. He is part of something called the Multi-Council Working Group, which is part of the BRAIN initiative at the National Institutes of Health. The Royal Society in the UK put out a big paper that looked at some of these issues. It is, if not front of mind of all the scientists, it is on the mind of all the scientists. And, the good news is we've got some time because, as Amy said, we're a ways off yet from being able to read or write complex thought. But as I said at the outset, we don't have a great track record as a society of dealing with these kinds of things. When I lived in San Francisco in the 90s, when the web was first coming up and getting popular, and everybody was like, oh, it's going to remove all the barriers to publishing and everybody's going to be able to say whatever they want. And yeah, terrorists and racists are going to be able to say whatever they want and spread a lot of misinformation. And, nobody thought about that at the time, or at least not in the very enthusiastic milieu of San Francisco that I inhabited, did they? But there's time, but also the issues are huge and the technology is moving fast. So I think it's important that these groups are doing their work. And I believe that there's initiative and there's trying to be, Amy, is there some agreement that people can sign on to where they say, yeah, we're only going to do this for X, Y, and Z, and we won't use it for other things?
If there is, the name of it is escaping me right now, but
yeah, that sort of rang a bell, but I may have just made that up. But maybe that would be a good idea. On the other hand, once it's, as somebody said in the chat, once the horse has left the barn, what are you going to do? I mean, the scientists were cloning, they're using CRISPR to make children immune to HIV, and there's always going to be people jumping ahead and trying to do stuff that not everybody agrees is such a hot idea.
That is a good analysis too, of thinking about the policy, getting ahead of the science and having policy people embedded within the science and add them to this interdisciplinary team. And thinking also, a lot of my work recently has been through the lens of eugenics and the eugenics movement. Obviously CRISPR is where I initially directed a lot of research and look. But in our discussion right now, I'm also, and Paul, you just brought up CRISPR, thinking about what some of the neuroscience and some of the companies want to do, which is essentially make better humans through this idea of better memory, or could you enhance cognitive abilities? Well, that's exactly what eugenicists who didn't have this tool were trying to do more than 100 years ago. And always imagining if this gets into the hands of people, which once that horse has left the gate, I think, as you said, right, it's the question is, where can we try and build in safety protocols? And of course, this is going to, all these technologies and applications are going to have bad actors accessing them. And well, we just can't treat it as if all panacea, but it's promise and peril along the way. And there's a question in the chat that I think we'll get to, and then we'll open it back up to some raised hands. We have about 6 more minutes, because I think this is a great chance for Terry Rankin's question, because it's really, really detailed, but I think we've got Amy here, and what a great opportunity. The question is the machine purpose function interface to individual will and intent the core of the cognitive problem? If not, what similar terms would you use to describe it?
Could you repeat?
Kind of this, I think the term that is, the question is around the term machine purpose / machine function. And the interface to, I think it's this idea of individual will.
I see.
And the terminology, yeah.
Sure, yeah. So I think that, I guess the thing I'll point out here is that I work specifically on brain-computer interfaces for restoring motor function. And there, I like to think of the device ultimately as, in some ways, kind of rerouting information, right, in the brain. So rather than when you think about moving, normally it travels through your spinal cord out to your muscles, and your arm would move. But instead, what we're doing is, when you think about moving, we reroute those signals, right, so that it now moves a computer cursor, for instance. So the device itself in that case, in that example, doesn't really have kind of an intent, right? It's sort of just wires, right? We're kind of just rerouting how information is flowing through the system. Where things start to get a little bit more tricky is when you have then like a machine learning agent, right, within that, somewhere in there, where the algorithm now is adapting in some way, trying to change that mapping, right? So now it becomes kind of an agent that's separate from you, and maybe that's kind of, I think that might be kind of at the core, somewhat related to this question. And so that's where then these questions about like agency and other issues in brain-computer interfaces start to get very interesting when you sort of have these multiple actors of the individual who may have one intent, and then kind of the device that has a slightly different intent. And so I don't know if that exactly answers the question, but I hope that it's in the flavor.
Great. Well, I think we are coming to our completion. I'm going to throw it back over to Hallie, and I have to thank everyone for all these great questions, and the chat is alive and well, and really great to be a part of all these new ideas and discussions.
Thanks, Dawn. And thank you to Paul and Amy for this conversation, and thank you to Dawn for stewarding us through it. Don't forget to register for our upcoming program on November 12th. And last but not least, thank you to all of you, members of the Bulletin's community, for participating with us this last hour. Ladies and gentlemen, we are adjourned.